So, part two of our notes here talks about direct substitution for polynomial functions and rational functions as well. So, p of x here just represents some type of polynomial function. A linear function, quadratic, x squared plus 3x minus 6, 2x minus 4, anything like that. So the limit as x approaches c of any polynomial function is just going to be that function evaluated at that value of c. The same thing can hold true for a rational function, all right? Where maybe we've got something like x minus 2 over x plus 1, so that's a rational function. So as long as whatever value that our limit is approaching in terms of x, as long as that value doesn't cause our denominator to equal 0, then we're fine, we can do that direct substitution, okay? And so that's what we'll start to see more of as we go along. If we're looking at the limit of a radical, that's fine, we're allowed to do that. If our radical is some type of odd root, okay? So we can see here the limit as x approaches c of the nth root of x. That's going to be the same as when we evaluate it, that will give us the nth root of c. The thing you have to watch out for is this. If it's an odd root, then whatever the value of c is, it shouldn't matter at all. Okay? If our root is even, then the value of c is very important. That value of c has to be greater than 0. Okay? Probably equals 0 as well, because we can have a limit that approaches 0. That should be fine. So greater than or equal to 0, we should be good there. If it's an odd root, cube root, fifth root, seventh root, whatever, the value of c is not as important. Okay? And so we can do some direct substitution. You'll see that some examples coming up here as we go. Limit of composite functions. So if we have two functions, f of x and g of x, let's say that as x approaches c, the limit of g of x is L, and then as the limit of f of x approaches L, then that limit would be f of L. So then when we take a look at the limit of the composite function as x approaches c, so notice here, the first function g of x and our composite function are approaching the exact same value. So we're saying essentially that we're evaluating f at the limit of g of x, which will give us f of x evaluated at the limit L. So it probably sounds like a little bit of gibberish there. How does it actually work out? So I gave an example here. So 3x plus 2 will serve as our function g of x. The limits of, we're going to take the limit of that as x approaches 2. And so if we do the direct substitution, because this is a polynomial function, 3 times 2 is 6, plus 2 is 8. So 8 times is our limit that we'll call L. All right. So that's what our second function, f of x, we're going to look at the limit of that function, x minus 4, as x approaches 8. So notice this 8 is coming from our previous limit. So I'm going to take and substitute that in. 8 minus 4 is 4. So essentially, our limit here is equivalent to the function evaluated at this value 8. So if I look at the composite function, think about it. So composite function, we're looking at f of g of x. So if I take my 3x plus 2, and I find that composite function with f of x, so that 3x plus 2 goes in for x, substitute that in. This would give us 3x minus 2. Substitute that 2 in, we get 6 minus 2 is 4. Notice that that's the exact same thing as what we had right there. So that's where that's coming from. Hopefully that makes sense. That is part 2 of our notes here because of our video issue. We'll come back with part 3 here in a moment.